I can. Can you guys hear me okay?
Yeah, sure.
Great. Good news. Well, it's a pleasure to speak today, and uh, my intention today is to give a bit of an introduction to who quantum brilliance is, but more broadly talk about diamond quantum technologies as a different technology vertical in quantum technologies, one that spans across sensing, computing, and communications, and one that is also particularly relevant to distributed, mobile, and integrated systems, which is hopefully on theme for the conference.
Hi,
And
hi.
so,
Sorry for disrupting you, Marcus. Are you sharing your screen?
not yet, but I will
Okay.
in a sec. I'll share the screen. Um, the title of my talk is going to be um, uh, an introduction to what is emerging as the diamond integrated quantum chip revolution. So this is a new suite of technologies, of quantum technologies enabled through the advent of integrated quantum devices based upon diamond. And as I said earlier, this is across sensing, computing, and communications. And it's not just quantum brilliance. There's about 40 to 50 companies worldwide who are now building a variety of different diamond quantum technologies. So, as I said, I'll first talk about quantum brilliance as an example of one diamond quantum technology company. And then I'll talk about the broader diamond quantum technology industry and where it is leading. So quantum brilliance, we're a spin out of the Australian National University, as well as the University of Stuttgart, in both Australia and Germany. So that comes off the back of around 20 years of research in developing qubits in diamond and a variety of diamond quantum technologies. For example, I began building quantum technologies in the early 2000s, building single photon sources for quantum key distribution systems. And over the last 20 years, there's been an explosion of development and research in quantum content. Quantum Brilliance is a company of around 90 people. So we have 45 people in Australia and 45 people in Germany. And we have a couple of different locations. So in Australia, Canberra, this is where we build our current generation of quantum computers. In Melbourne, this is where we are establishing a materials foundry to synthesize the advanced materials required for diamond quantum technologies at pilot production scale. And in Germany, this is where we are doing the research and development of integrated devices, combining diamond with integrated micro electronics and photonics to make these manufacturable technologies. And so we've partnered with research institutes around the world, primarily in Australia and Germany, but we also have deep relationships with laboratories such as the Oak Ridge National Laboratory. Quantum Brilliance was founded in 2019, and over the last 5 years, sort of developed three core capabilities. One is around diamond materials, so this is creation of the qubits in the diamond. Another is around integrated devices. And the last is around building complete systems and integrating those systems. For example, we have built complete quantum computing systems, and we've integrated them into supercomputers. People can utilize those computers as part of the mix of a high-performance computing system. But if you ask me what really makes us different, what are those technologies that are unique to us, then they're really about the integrated device. So working from the left, it's really around these very high-quality diamond materials that we synthesize, the ability to place qubits with sub-nanometer precision at 5 nanometer pitch using this atomically precise qubit fabrication technique, the ability to engineer these electro-optical devices using nano electronics, photonics, and microelectronics, and the capacity to design these integrated devices. So that's kind of what really sets us apart within the diamond field is this engineering. And so if you were to ask, what does quantum brilliance do? This is the system. We've used that to do a variety of sort of important milestones. So In 2022, we deployed a quantum computer into the Supercomputing Centre. It's a tier 1 supercomputer here in Australia. We demonstrated a mobile quantum computer in 2023. 2025, we just shipped a cluster of 3 quantum computers to Oak Ridge National Labs. So these are 3 computers, each with a GPU, a CPU, and a QPU. And those 3 computers are then connected together. And the idea is that Oak Ridge National Labs will use that as a platform to test different ways of hybridizing and parallelizing quantum and classical computing in order to inform architectures, so high performance computing architectures for hybrid and parallel quantum computing systems. So that's the purpose of that system that we're delivering to Oak Ridge. And we've gained a contract from the German Cybersecurity Agency to deliver our kind of end vision, which is the thing that has always driven the company, which is a GPU-size quantum computer in 2021. And so that's kind of really what drives our technology, is that vision of delivering a GPU-sized computer. Then the German Cybersecurity Agency has a variety of defence and national security applications that are seeking to exploit that compact quantum computer. So that's a bit about quantum brilliance, but let me now talk about a broader introduction to diamond quantum technologies. So as I said earlier, there's about 40 to 50 companies worldwide developing diamond quantum technologies. These range from large multinational companies such as Bosch. The majority of the large defence corporations such as Lockheed, L3Harris, Thales all have diamond quantum technology programs. But then right through to smaller companies such as Quantum Brilliance and small startups as well across the world. Notably, Fujitsu is the leader in the development of cryogenic-based diamond quantum computers. I would hope that Quantum Brilliance is the leader in the development of room temperature compact diamond quantum computers. And then there's a variety of those other companies there, which I'll get to and talk more about in a second. What enables all this to happen is the nitrogen vacancy center, which is an engineerable qubit, which operates entirely in ambient conditions, can also operate at cryogenic conditions, has exquisite properties, which I'll talk more about in a second. But because it's engineerable in a variety of device architectures, you can make a variety of technologies across the communication sense. And diamond quantum technologies are relatively mature. There is already high TRL prototypes or proto products. So on the top here, we have Bosch. They've created a Raspberry Pi-sized quantum magnetometer. That's an example of a product which is about to go into production. You have Sandbox, who have created a quantum magnetocardiogram that, again, that's currently being trialed in various hospitals. You have these quantum microscopes being developed by companies like Konami, which are now being tested in foundries for semiconductor inspection. You have our early quantum computing prototypes and Fujitsu's quantum computing prototypes, which are being used by a variety of customers and partners. And indeed, LightSync was just acquired by IonQ for their quantum internet technology as part of communication between quantum computing processes. So let me give some examples about, what makes diamond quantum technology so different. So I showed before that, hey, one of the differentiators is the diversity of technologies that originate from this one qubit. The fact that it can be compact and miniaturized and manufacturable, such as the Bosch example at the top. But where does that lead to? Well, where it leads to is applications where quantum technology needs to be compact, miniaturized, and manufacturable, in particular where you need mass deployment of that technology. So let me now talk through some examples. So a good example is navigation without GPS. So this is an example of magnetic navigation. So this is where you use a very precise magnetometer, like the one developed by Bosch or Phasor Quantum, and you measure your local magnetic field. And you compare that magnetic field against a map of the Earth's magnetic field. And then combined with an inertial navigation system, you can then do precision navigation. And so this is an example of Phasor Quantum, who used their diamond quantum magnetometer on a US military aircraft. And when combined with an INS system and flown across the Pacific, it maintained better than 100-meter positional accuracy for that flight across the Pacific, which met mission requirements. And so this is a real testament that this is a real technology that's delivering real mission, which is meeting real mission needs. And that is not an application where there's going to be one plane that needs it. It's an application where all defence and civilian aircraft will need it, and one day potentially maritime. So this technology. So it's not ones or twos, it's tens and hundreds of thousands of these devices. Another one is quantum machine learning. So I think often when we think about quantum machine learning, we all sort of pretend not to understand the real problem, which is to really do training at scale. You can't just have one or two quantum computers. You need hundreds and thousands of quantum computers that operate in parallel in order to genuinely be able to train sophisticated neural networks. And then there is then of benefit, obviously, that beyond the restricted set of applications where you can poll a centralized data center, but where you actually need to have distributed computers who can do inferencing, then you also need quantum computers that can read. So, for example, we've done work with Lockheed Martin, in particular on the bottom right-hand corner, which is around quantum machine learning for synthetic aperture radar. So identifying features such as identifying ships in synthetic aperture radar images, which have been taken by satellites orbiting the Earth. It's a great example of where the strength of quantum machine learning correlates with the paucity of data and the limitations on training cycles, and also one where it is advantageous to have the quantum computing deployed on satellite in order to do the pre-processing communicating. Further examples, so one here is using diamond quantum nuclear magnetic resonance spectrometers in order to perform pathology tests. So a company called Phoebe is developing a technology where they can perform a variety of chemical analysis of blood at the point of care using a compact system by exploiting diamond quantum nuclear magnetic resonance spectrometers. So this is also a great example where if you can fuse a diamond quantum processor with a diamond quantum nuclear resonance spectrometer, you can really enhance this task, which is you can perform classification of the signals detected by the spectrometer in order to identify what chemical species are present or absent from the blood sample. Indeed, this is something that's already been demonstrated in diamond quantum tech, where a diamond quantum processor has been used to perform spectral analysis on incoming signals by using quantum Fourier transform-like methods to perform that spectral analysis. On the right-hand side, this is around the idea that another thing which is also well known is that you can culture neurons very well on diamond. And so there's a picture on the bottom right-hand corner of neurons who have been cultured on diamond chips containing qubits, and then those qubits have measured the functional neurosignals firing between those neurons and those chips. And so there's a company called Chromos, which is now seeking to build a scalable platform for the development of neuromedicines, where they are using these diamond chips with these embedded diamond quantum sensors in order to functionally measure the behavior of neuron or the response of neurons to different types of drugs in order to aid the development of those drugs. So I mentioned that this is all possible because of this qubit platform called the nitrogen vacancy setup. Um, in many ways, it's an exquisite platform. At room temperature, you have incredibly long coherence times of greater than a millisecond, which is essentially at least 1,000 times longer than superconducting qubits that who operate at millikelvin temperatures. You achieve very high fidelities. So initialization and readout fidelity is greater than 99%. 2 qubit gates of fidelity greater than 99% have been demonstrated. Single qubit gates of 99.99%. And you have this sort of intermediate speed shot rate, which is between a kilohertz and a megahertz for gate times and shot rates. You've also got the fact that you can create, have an atomic-sized qubit. We create millions of these qubits in devices and integrate them with electronics and optics. It's really what has been the big blocker for Diamond has been really a question around fabrication, which is really being able to fabricate these devices with precision in order to, say, scale the number of qubits in quantum computers, improve the precision in quantum sensors, and then not only do that, but then also integrate them in a way that they're manufacturable such that they can actually deliver against those use cases for which they promise. And so the advent of the integrated chip is really the critical next step for diamond quantum technologies. And what this slide seeks to show is that whether you're building a sensor or a computer, it's really this chip is what's the big important next step. And this chip has a bunch of common components which are arranged in different ways, depending on whether you're building a sensor or a computer. And what this has led is that the diamond quantum technology industry has led towards actually defining a roadmap for these chips. So what I give here is a high-level summary for the roadmap for diamond quantum chips. Where we are today is what has been called a type 1 technology. So this is characterized by using fairly basic diamond materials and completely optical initialization and readout. What is needed next is to move to a type 2 chip, which is now where you're a more sophisticated functionalized diamond and precise diamond combined with electro-optics. And then finally, a type 3 chip where you have this nanometer fabrication, precision, and integration. And you unlock different performance and also different technologies. So the role of Quantum Brilliance is we really see ourselves as the company that has the technologies that unlock these type 2 and type 3 chips. So those core technologies being what I showed you earlier in the presentation. So we see our role as really supporting the development of this chip and being the chip company diamond quantum technology. And to give you some examples about why this is important, if you move to a type 2 chip, then you can get a 10 to 100 times performance advantage for, say, quantum sensors. So this is in particular talking about an improvement in sensitivity, but also there's a reduction in size, weight, and power. It also comes with these technologies. So sort of roadmap for the future. This year for Quantum Brilliance is really about demonstrating all those core ingredients that I showed you earlier on the slide. We're also releasing a simulation tool that allows you to design integrated devices for diamond quantum technology. Next year, we are seeking to demonstrate a scalable quantum computing chip of 10 plus qubits, as well as releasing a quantum sensing module and also releasing type 2 diamond materials to customers within the diamond quantum technology industry. 27 to 28 is then when we're looking to get to that chip scale or system and package scale more accurately, quantum processors and sensing modules. And then that 2030 to 2034 is then when we're moving towards fault-tolerant devices. And so to put some qubit numbers on this, for quantum processors, we're really looking at 64 qubits in 2028. So that's 64 physical qubits. And in 2030, in 2034, that's when we're looking at 64 logical qubits. So while these qubit numbers are not the qubit numbers you see in what we would call mainframe quantum computers, you have to remember that these are a chip scale solution, which so be compatible with a quantum computer the size of a GPU. And so the motivation isn't to outcompete a supercomputer with one of these chips. The motivation is just to outcompete a single GPU with one of these chips. And so we believe that around that 64 logical qubits is then when we'll see a genuine performance advantage pound for pound with GPU and other classical accelerators of similar size, weight, power, and cost. All right, so what can we do in the intermediate time? So feel free to reach out to us. We're very happy to talk to people interested in alpha and beta release of our device simulation tools. We already have what we call a virtual QPU. We were one of the first software partners of NVIDIA in Quantum CUDA, and we've also worked with Oak Ridge National Labs for a long time on developing a variety of quantum software. So feel free to go to our website. You can download our SDK, or you can download our vQPU. The SDK is geared towards enabling you to really test and trial parallel and hybrid computing. So you can, to a high degree, control distribution and synchronization of computing tasks between classical and quantum hardwares. And the vQPU is that emulator, which then really sits as a representation of our current and also future hardware, which includes noise models, timing models, scheduling models, and these sorts of things that allow you to really simulate what it would be to integrate one of our chips into a computing system. And so with that, I'll draw to a close and open up for questions.
Can I ask a question?
Yes, please.
Okay, so you mentioned that you guys are doing room temperature development of color centers, but under room temperature, how do you guys control the phonon noise? Especially you are using NV centers, but not silicon vacancies, so that you don't have the symmetry.
So silicon vacancy centers are actually much more susceptible to phonon noise than NV centers. So
Yeah,
I
but I mean,
was
how do you guys control the phonon noise in room temperature?
Yeah, so the phonons interact with the NV via spin phonon interaction.
Yeah.
The spin phonon interaction is incredibly weak at incredibly weak for the NV center. And secondly, because of how hard diamond is, the actual density or the number of phonons at room temperature is very low. And so NV center has been known for 20 years to having these millisecond coherence times at room temperature. It's not a new phenomenon. And it's a combination of that weak spin phonon interaction and the small number of phonons which are available at room temperature in diamond because of its hardness.
But that phonon spin interaction will give you spectral diffusion that will limit your interaction of different NV centers, right?
So it doesn't give you spectral diffusion. So spin phonon interaction gives you a homogeneous dephasing and relaxation, so it contributes to T2 and T1. So it doesn't interfere with your interaction between NV centers. So again, these are things which are well documented in literature, where you can quite nicely control multiple NVs which are coupled together. And you can achieve very high gate fidelities with these NV systems.
But I mean, you said that it will not introduce the spectral diffusion, but how do you get rid of this inhomogeneous burning?
Well, we don't need to because it's so little. So as on the slide, your coherence time is better than a millisecond. So it's of negligible effect.
Yeah, I'm talking about two NV centers. How do you do the interaction between them? If you have the room temperature, they have broadening, so they are so broad.
Oh, okay.
Yeah.
No, well, they're not broad. So as I said, the coherence time is a millisecond. So the way they interact though at room temperature is magnetically. So you place two NV centers close together and they directly magnetically interact with each other via the spins. I think I now understand where you're coming from. You're coming from the architecture where you have a optical interface between the NV centers.
Exactly.
Okay, so you have to be cryogenic to do that. But that's not what you do at room temperature. When you build a room temperature diamond quantum computer, you place these NV centers very close together so that they directly magnetically interact.
I see. So you do not need to rely on the spin photon interactions. Okay, I see. Thank you. Thank you.
And I completely agree with you. The optical transitions are very broad, and there is spectral diffusion in those. Here I was referring purely to the spin.
I see. Thank you. Yeah, appreciate it.
I think this is a wonderful thing that we're just talking about room temperature qubits. But come from computer science background, as you're answering Japon's question, I have the same question. I was wondering what is the secret sauce? Because in quantum computing, there is always this kind of tension between you want to have control and also you want to have isolation with the environment, right? Sounds like you could have good control while with very strong isolation from the environment at the room temperature. Could you maybe at a very high level explain to a lay audience how you achieve this in your technology?
Yeah, so hey, the challenge for diamond the challenge for diamond quantum technology is the fabrication. So where's the best slide here? The challenge is when we're seeking to say build a quantum computer, we need to be able to lay these NV centers out at a 5 nanometer pitch, and with a better than 1 nanometer positional accuracy. And we need to be able to interface electronics and optics with these NV centers. And so this is not easy. So whilst the individual qubits are exquisite, they're exceptionally good, and at room temperature and pressure, they have these remarkable coherence properties. It is a significant engineering challenge to be able to fabricate the devices in order to enable that scale. So this is the challenge.
I see. So is that basically how you achieve that? Is basically by physically position the diamonds precisely on the atom level. That's how you are able to achieve the strong isolation and still you can control it, right? Is that the
Exactly. So the NV centers are intrinsically this very well isolated system. That's a combination of the NV internal properties and also the properties of diamond. The fact that diamond can be incredibly chemically and isotopically pure, that it has this very low phonon background because it's very hard. So there's these intrinsic properties. But then to engineer a technology, you need to then be able to fabricate these qubits in a way that you can make a functional device. And so, what quantum brilliance is focused on is this nanometer precision fabrication of the NV centers. It's being this is the secret sauce. This is the way that we're seeking to overcome this challenge.
Thank you.
I have a question on the scalability. Like, what's the fundamental limit of scaling diamond based? Like, why can't we go for like 1,000 qubits?
So can certainly go to large qubit numbers. It's all about this fabrication yield. So right now we have low yield, so we have low qubit numbers. So there needs to be improvements in these fabrication techniques to be able to scale to larger numbers. And there needs to be, when you get to large enough arrays of these NV centers, then there has to be alternate ways of laying them out such that you can adequately control all of them. And so as you get to a large enough scale, which is when you're about 100 plus physical qubits, there is then another layer of complexity you then need to manage in how you design these devices. So there's some of these important things to get through as we scale up.
Thank you.
do you mind me asking another question? Sorry.
Yeah, sure.
You mentioned as magnetic field control and the color center to color center interaction. So usually these are very localized interactions. So compared to this, optical interaction, you can go from fibers all very, very long. Then if you are going to build such a quantum computer using this very localized interaction, are you also looking at similar technologies like transmon use? Because you can only have adjacent entanglement or quantum interactions.
Yeah. So if I understand your question, so that the connectivity in these computers
Exactly, connectivity issues.
will be nearest neighbors. And so it will be a two-dimensional layout of the qubits, and there'll be nearest neighbor interactions in that two-dimensional layout. So there is different options. There's a square lattice or a hexagonal lattice of how these qubits are then labeled.
I see. So following technical question. So is this interaction similar Rydberg atoms like decay very fast at a distance?
Yeah. So it's 1 on R cubed.
It's exactly at Rydberg atoms. Okay. Thank you.
Rydberg it's an electric dipolar interaction. In our case, it's a magnetic dipolar interaction.
Okay, makes sense. Thank you.
Thank you very much. And our last speaker is our invited talk from Professor TU Delft, Przemysław Palczyk. I hope I pronounced it correctly.
No.
Sorry.
No problem. Perfect.
Yeah.